In this video, we now define what is known as the gamma distribution. And it is another very important distribution. I wouldn't say it is as important as the Gaussian distribution, but it's definitely up there. And it has some distinct differences when compared to the normal distribution. So I think it's good for us to see a variety of these special continuous random variables and be able to compute probabilities and understand a lot of properties of the distribution. All right, so let's take a look at the definition of the gamma distribution. So a continuous random variable x is said to have a gamma distribution. All right, so let's underline that if the PDF of x is this function. All right, and it's a little messy, right? So here's our piecewise function, and it is 1 over beta to the alpha times gamma of alpha times x to the alpha minus 1 times e to the negative x over beta, and this is valid when x is greater than or equal to 0, and then it's 0 otherwise. Right? Well, and so what are all these letters? Well, the gamma here is the gamma function that we previously defined, and then alpha and beta are the parameters of this distribution. So where the parameters alpha and beta satisfy this property. They both have to be positive numbers, right? Right, so alpha and beta have to be greater than or equal to 0. And if beta is equal to 1, then the distribution is said to be a standard gamma distribution. So if beta is equal to 1, we have a standard gamma distribution. Right, so it's just a special case. In fact, there's another special case when alpha is equal to 1, and again, that will be handled in the future. Right, so if beta is equal to 1, then we have a standard gamma distribution. All right, so so a couple of things to note. Yes, the parameters are important, right? But notice here our sample space is now all non-negative real numbers. So unlike the normal distribution, where the sample space is the entire real line, now we're essentially just dealing with the non-negative portion of the real axis, right? Now, there are some other important differences between gamma distributions and Gaussian distributions, and I think the differences will become very apparent if, again, I just highlight some of the key things from a graphical standpoint, right? Again, we're not going to derive a lot of these properties analytically just because of the improper integrals and the integration by parts. It's not difficult, but it's extremely time consuming, very tedious, right? But let's just look at the sketch, for instance, of some of the gamma distributions. So since they are defined for x greater than or equal to 0, I'm just going to draw a couple like here. So here's our x-axis, and I'm just going to sketch the PDF of a few of these, right? So if, for instance, if alpha and beta are 1, you're going to end up with a graph that looks kind of like this. It starts out here, and then it just kind of tapers off like that, right? So this one, so I just wanted this kind of as a reference point, right? So this is what you would get if, for instance, alpha is equal to 1, beta is equal to 1, right? If, let's say, alpha is equal to 2 and beta is like a third, it's like a proper fraction. So if alpha is equal to 2 and beta is equal to 1/3, you would get something like this, where it would peak up and then it would come back down pretty dramatically and then taper off like this, right? So this one would be an example of something that where your alpha would be 2 and beta would be something like 1/3. What if alpha and beta, like alpha is 2 but beta is 1? So if alpha is 2 and beta is 1, then you're going to end up with something that looks like this, where it's kind of a little bit flatter, goes up, comes back down, looks like this, right? So this would be an example of something where like alpha is equal to 2 and beta is equal to 1. What if they're both 2? So if alpha and beta are 2, you're going to end up with, again, something that looks kind of like this. It goes up and then again tapers off like this, right? So that one would be where your alpha is 2 and beta is 2. So what is very clear just by these 4 examples is that your gamma distributions are not symmetrical, not like your bell curves, right? So gamma distributions, or gamma random variables, however you want to say it, so these distributions are not symmetrical. In fact, they're always skewed to the right. So they always peak early and then they taper off and they have these tails and so forth. So they are all skewed to the right. And they are helpful in modeling things, modeling measurements that it's highly likely that you'll have small measurements, right? And very unlikely that your measurements will be big, but they allow for the larger than usual measurements. So things, for instance, like the lifetime of a bulb, right? You can model it using like this. Obviously, your lifetime is not going to be negative, so the fact that it's defined for non-negative values of x, your lifetime would be something like that. Insurance claims as well. Insurance claims, they tend to follow these distributions that are skewed to the right. And again, one example of such a distribution would now be the gamma distribution. There are other ones out there, right? But this is just a very popular one that has some very basic applications that are really useful, right? So again, they always peak early. Some of them, start out and then they decrease. Eventually, they always decrease, and they're always asymptotic to the x-axis, right? So they are all asymptotic to the horizontal axis. All right. So those are just a couple things, and again, the beta and the alpha, again, you just changing these, it affects where the peak occurs, and then also for instance, like this particular curve here where your alpha and beta are equal to 2, you can see that it has an inflection point because it's concave down here, and then all of a sudden it changes and it becomes concave up. So for instance, the location of the inflection point along these gamma curves are also affected by alpha and beta, right? So again, we could do a really detailed analysis, but that's not our goal here, right? Okay, so we have the PDF. In general, there is no nice formula for the CDF of the gamma distribution. And there also, we don't have tables as well, because it's not, there is, even though you might have something called a standard gamma distribution when your beta is 1, it still allows for lots of different values of alpha. So it's not standardized the way like the standard normal distribution is. It's standardized in the sense that, okay, one of your parameters is fixed, but you can still allow the other parameter to vary, right? So we don't have nice tables for this. So we are going to end up having to do a bit of calculus here. And what I would say is this: the gamma distributions, particularly the ones that we're going to focus on, they're kind of in the middle in terms of difficulty. Again, think of think of like a spectrum that represents the difficulty of integration. You would have the uniform distribution on one end being the easiest, right? And then the normal would be on the complete opposite end. That would be the most difficult because we can't possibly compute the integrals. We always have to rely on tables or software. The gamma distributions, they tend to be somewhere in the middle. A few of them are fairly easy to integrate, right? And again, those are the ones that we're going to focus on, right? But we still have to end up using things like integration by parts. Before we look at a specific example, I just want to mention the formulas for the mean and the standard deviation. So, and some notation. So if x has a gamma distribution, right, with parameters alpha and beta, this is how we're going to write it. So, and this is where we have to be careful. So x, so this will now tell us that it's a random variable that has this distribution. We're going to still use our gamma notation here, right? And then in parentheses, we'll have the alpha and beta. So the alpha is always going to be first, the beta is going to be second. Otherwise, we could just write it out and say that x is a gamma random variable with parameters alpha and beta. And now let me give you the formula for the mean and then the formula for the variance. So it turns out that your mean or your expected value, it's not difficult to prove. It just relies on a bit of integration by parts, but you end up getting that the expected value of your gamma random variable is simply alpha times beta, right? So just multiply the parameters and you'll get the expected value. And your variance is equally easy. It's alpha times beta squared, right? And again, these are results that it would be interesting just to look at the math that goes into it, but we're not really going to gain much from going through the integration by parts. All right. So let's do an example. Just going through computing, certain probabilities, expected values, and so forth. So let's look at an example of this. So let x be gamma with parameters 2 and 10, right? So first of all, let's practice writing down the PDF because we're going to rely exclusively on the PDF for all the probabilities that we have to compute. There is no CDF, there is no table, right? So let's write down what the PDF will be. So it's going to be piecewise, and the formula is, so let me just make a note here that alpha is 2 and beta is 10. So it's 1 over beta to the alpha, so it's 10 squared, times the gamma of alpha, so the gamma of 2. So that's essentially the constant that we need to make it a valid PDF. And then it's times x to the alpha minus 1 times e to the negative x over beta. And this is for x greater than or equal to 0, and then it's 0 otherwise. All right. Well, let's simplify this. Now, previously when we talked about the gamma function has this property that if you're taking the gamma of a positive integer, it is the integer minus 1 factorial. So this is going to be 2 minus 1 factorial, and that will be 1 factorial, which is 1, right? So this factor here, or this term, is equal to 1. Everything else simplifies normally, right? So in order to get this to a point where we can get a function that we can actually integrate and work with, then we will be using this result many times, right? So here is kind of the simplified form of the PDF. So we have 1 over 100 times 1, so that's 1 over 100. And then we have x to the first power, so that's just x. And then we have our e to the, I'll write it like this, negative 1/10 x. So that's our PDF. And it's valid for x greater than or equal to 0, and then it's 0 otherwise. All right. So there is our PDF. So let's just go through and compute certain things. So let's say we wanted to find the probability that this gamma random variable is between 2 and 5. So let's say it's like this, right? Since there is no CDF, we're going to have to rely on integrating the PDF. So this is the integral from 2 to 5 of 100x e to the negative 1/10 x dx. And because of this product right here, we have to use integration by parts. And in this, for this particular example, I'm going to go ahead and use my table. I like using the table form when I have like a polynomial times an exponential. So I'm going to I choose my u and dv the same way that I do normally. I'm just going to do it in a slightly more efficient way. So now what I can do is I can keep the 100 here, or it might be easier to factor out the 100 and just focus on the x e to the negative 1/10 x, right? So take out the constant and just focus on these two functions. So I'll choose x to be my u, and then my exponential to be my dv. So using the table method, you differentiate your u repeatedly, and if you have a polynomial, you can continue to differentiate it until you get 0. And then you integrate your dv repeatedly. So if I integrate this repeatedly, I'm going to end up getting negative 10 e to the negative 1/10 x, and then now a positive 100 e to the negative 1/10 x, right? And now how do I use my table to get my antiderivative? Well, we form these products. And formally I should, so each of these is a uv. So this is u times v, and then technically I'm supposed to integrate the product here going across. This would be my v du. So v du would be this one, and I should integrate it. But the problem is, well, not the problem, in fact the good thing is that this factor is 0. So I end up integrating 0, so I can essentially ignore that part, right? And then the last thing I have to make sure is that I alternate the signs here, right? So looking at this table, I can write down my antiderivative like this. So it is, so I'll put it in square brackets. So it's a positive x times this negative 10 e to the negative 1/10 x. So I have negative 10 x e to the negative 1/10 x, and then minus 1 times a positive 100 e to the negative 1/10 x. So I end up with negative 100 e to the negative 1/10 x. And again, I can ignore that part because that would essentially end up giving me my plus c, but I don't need my plus c because I have a definite integral. So this is from 2 to 5. All right. So again, a couple things we could do that might help. Seeing that we have the a 1/100th out here, if I were to distribute it, it would kind of simplify things a little bit. Or if you want to keep the 1/100 outside, you can certainly do that. But don't forget that we have to multiply it by this 1/100 at some point. Otherwise, we're not going to get a valid probability. So let's start with the upper limit and plug the 5 in. So this will give us a negative 50 e to the negative 1/2 minus 100 e to the negative 1/2. So that's at the upper limit. And then minus at the lower limit now, we're going to have a negative 20 e to the negative 1/5. And then minus 100 e to the negative 1/5. All right, so let's so the way this works out, we have like terms here that we can combine, and we have like terms here that we can combine. So I still have my 1/100 in front. So here I would have negative 150 e to the negative 1/2. Right. And then let's see, so then this would be negative 120, but then there's a negative outside, so a positive 120 e to the negative 1/5, right? And then when I distribute the 100, and now what I'm going to do, I'm going to write the positive term first. So I would have 120 over 100, well that's 6 over 5, so this is 6 over 5 e to the negative 1/5, and then I'd have minus 150 over 100, and that would be minus, so that would be 3/2, and then I have e to the negative 1/2. And at this point, I mean, let's just, so if we get the decimal approximation for this rounded to 4 decimal places, we're going to get 0.0727, right? So just over a 7% chance that this gamma random variable, right? This gamma random variable will take on a value somewhere between 2 and 5, right? So that's that particular probability. Let's say we have another probability now. Let's say we want to find the probability that this random variable is greater than 6, right? Well, we kind of have the PDF here, right? But now we'll be going from 6 to infinity since the sample space is unbounded on the right? So we would end up having this from 6 to infinity, and then we would integrate the function 1/100 x e to the negative 1/10 x dx. And if we keep it like this, then we would always, we would have to treat it as an improper integral. So we would have to first do from 6 to b and do well, we've already done the part, so at least we have the antiderivative. But if we have this upper limit of positive infinity, then we would always have to use our process for an improper integral. But why not use the complement? You see, because the sample space of a gamma random variable is from 0 to infinity, we can always deal with just a finite integral if we use our complement rule on something like this. In other words, instead of doing this, just say this. The probability that x is greater than 6 is 1 minus the probability that x is less than or equal to 6. But the lower limit on a gamma random variable is always 0. It's not like the negative infinity in the normal distribution, where you'd always have to start from negative infinity and integrate up to a particular point. No, we can, in this case, we would end up having 1 minus, and then the integral now would go from 0 to 6, and it's no longer an improper integral. So with the gamma ones, even though, yes, we do have to do our integration and so forth, but we can always avoid having to do the to compute probabilities where the upper limit by definition would be infinity. We can always use our complement rule and avoid that, right? Okay, so we already have the antiderivative here. So then this will be, so let me kind of go back up. Where is that antiderivative? It is right here. So it's the negative 10x e to the negative 1/10 x, and then minus 100 e to the negative 1/10 x. So let's write that down. So we have the, let me put the 1 over 100 there, and then we have that, what did we say? Negative 10x e to the negative 1/10 x, and then minus 100 e to the negative 1/10 x. And now my limits are from 0 to 6. All right, pretty sure, let's just double check again. Yeah, there we go. So we got our right antiderivative, and now we're just going to evaluate, but then we have to remember to do our 1 minus, right? So let's see what we have. So negative 1 minus 1 over 100. At the upper limit now, when we plug our 6 in, we'll have negative 60 e to the negative 6 over 10, so that's negative 3/5. And then minus 100, same e to the negative 3/5, right? So we have that one. And then at the lower limit, so at 0, well, let's see what happens. Hey, this works out nicely because this term is now 0. And then e to the 0 is 1, so we end up with negative 100, like that. So just another benefit of using the complement rule. So then we have 1 minus 1 over 100, and then we have a couple, these are like terms again, so this is negative 160 e to the negative 3/5, and then plus 100. All right, well, look at that. Look at what happens here. Because if I distribute the negative 100 now, I'll have 1, and this becomes a positive 160 over 100. So what's that? 8/5. So a positive 8/5 e to the negative 3/5. And then this negative 1 over 100 times a positive 100 gives me a negative 1. So even the 1 cancels out. Man, that works out nicely. So this is our probability. This is our exact probability. Rounded to 4 decimal places, it is 0.8781, right? So almost an 88% chance that this gamma random variable, right, will exceed 6, right? So just a useful thing to keep in mind with the gamma, computing probabilities like this, there's always a way to avoid dealing with the improper integrals. Let's finish up by finding the 3 things that we always find for these random variables. Let's take a look at the expected value. Well, the expected value of a gamma random variable is always your alpha times beta. Alpha in this case is 2, beta is 10, so the expected value here is 20, right? The variance is always alpha times beta squared, so that's 2 times 10 squared, and that is 200. And then of course our standard deviation, so our standard deviation of x is the square root of the variance, and that's going to give us the square root. So our square root of 200, and that is, what would that be? 10 root 2, right? So I think more than anything, it's the one thing that's really new in this entire process is working with the gamma function to figure out what that value is in the denominator in our PDF, right? That's really the new thing. But for us, for us to be able to do a problem, the alpha has to be a positive integer. Otherwise, we're not going to be able to do, well, first of all, we wouldn't be able to evaluate this for the most part, and then the actual integration will be very, very difficult, right? So for us, our alpha is going to be a positive integer, and we'll be using this recursive property of the gamma function to help us evaluate this. But once we have this number, everything else is pretty much routine. There's integration by parts involved. Again, it might not be the funnest experience, but I don't know. I think integration by parts is pretty good. And then, evaluating. And like I said, this nice trick of using the complement to avoid dealing with the improper integral, that's always a handy thing to keep in mind. And then we have our formulas that if we need to, we can compute our mean, variance, and standard deviation. All right, well, that's our gamma distribution, and I'll see you in the next video.